We tag team this talk, which make it rather informal, but also ask for you to ask questions as we go. Like, don't be afraid to do that. Seek clarity. Talk's built on creating an understanding from the ground up, so there'll be people with different levels of knowledge about what we're talking about. We just start, so there's a foundation that everyone builds on. Okay.
Right. So I'm just going to start. I'm an agronomist, and Jason's a soil scientist. A soil scientist should not present anything without an agronomist in the room, and the same, an agronomist should have a soil scientist in the back pocket too. So this project, the results we're talking about today is a sort of culmination of a fair bit of work that Jason and I have been doing over the last few years. We have had a lot of trouble getting funding on soil acidity because everybody knows everything about it and people are using lime, so what's the problem? But we've managed to get funding through the National Landcare Program, which kicked off with some work done with Grassland Society of New South Wales and Holbrook Landcare Network, which Phoebe was involved with in previous life. And so in collaboration with those two, New South Wales DPI, which who employs me, and Jason for this part of the project, we have set up a number of sites from Holbrook, from near Canowindra and over towards Lyndhurst. And we're just getting through our second round of results, soil test results, to look at some of the impacts of the management strategies we've got in place. This next, the other logos up there, we've got additional funding from National Landcare Program to bring FarmLink, Central West Farming Systems on board, and we've got sites established down in the cropping zone. We've also got some LLS from the southeast involved, and ACT and RM. So we've got a number of sites across southeastern Australia. And more recently, and the funding we have today is through Newcrest Mining, who have, through their Cadia Community Partnership Program, we've been able to do a little bit more monitoring on some of the sites, the site at Tugong, near Canowindra, and the site at Lyndhurst. But having said that, and making sure that we covered off on all the sponsors that we've got, Jason's going to kick off with a little bit about some going back to high school chemistry and tying that in with some of the stuff that we've been doing in the field.
Right, so we're here to talk about acidity, and we care about it because it affects plant growth, right? That's fundamentally why we're interested in it. How it does that is by various means, but predominantly the big factor is aluminium toxicity. So aluminium's an element in the plant, in the soil. There's heaps of it. It's not always available to plants though, and so it can change forms, become available to plants. Plants don't need it, but at a high enough concentration it damages them. So we track it, we monitor it in soil by looking at percent aluminium. So this is a graph, percent aluminium and pH. So pH is basically how much acid's in the soil. The smaller the number, the more acid there is. And so in soils you normally get as acid as about 4 or just under 4. It doesn't get any more acid than that. The soil dissolves after that. So if you've got a pH of 4, measuring calcium chloride, that's as bad as it's going to get, right? After that, you can keep adding acid, it'll stay at 4, but the clays dissolve. Now, this percent aluminium, in soils, there are components that hold nutrients. So clays hold nutrients and organic matter can hold nutrients. So how much nutrient can be held, we measure that as cation exchange capacity. So nutrients in soils are cations, some nutrients in soils are cations, and they are stuck to clays and organic matter. So obviously we want to know, does my soil have a lot of that, or does my soil have a little bit of that? And so we measure cation exchange capacity. So in a way, it's like saying in this room, the seats would be the cation exchange capacity, the ability to hold nutrients, and all you would be the nutrients. So if you've got a soil that's got a lot of clay and a lot of organic matter, there's a lot of seats in the room, so it can hold more nutrients. If it was a sand, not so many seats, so you can't hold many nutrients. Okay, and this percent aluminium is saying what percentage of the seats have aluminium on them. With me? Right? So cation exchange capacity is just something we measure. You'd see it on your soil test results. The bigger that number is, ideally the more fertile your soil would be. And if the aluminium percentage increases, more and more of those seats are occupied by aluminium, which a plant doesn't need. And it can be harmful to the plants. Yep. Like I said, if at any time you're thinking, what the hell are you talking about? Just let me know, right? And we'll clear it up. So I'm going to show you a graph. They're the axes. So this is getting more acid. This is getting more aluminium that can hurt plants. Now I'm going to show you data that was taken from lots of places through New South Wales, cropping and pasture zones. So thousands and thousands of soil tests. That's what the data looks like. Okay. This is not just listen to me talk, this is interactive. What do you see there? What are the things from that data that stands out to you? Yep. So up here, we've got half the places that could hold nutrients actually holding aluminium that is no good to anyone and is actually dangerous. Yeah? Yep. What else do you see?
You get your pH of 5.5, that's virtually 0.
Yep. Okay, so there is none. There is no aluminium up here. And I've got a little blue line there that's at 5%. And roughly speaking, if your soil is below 5% aluminium, you can grow whatever you like, right? Most plants can exist in 5% aluminium without having massive yield decreases. Okay. Once you get over 5%, then the aluminium starts hurting plants. And some are really sensitive and some are more tolerant. So acid tolerant crops or acid tolerant pasture species are actually a little bit more tolerant to the aluminium. Okay, so there is none over 5.5, but really that line, there is none over 5% at about 5, pH of 5. Do you see it? Righto. What else do you see? There's two more things I want you to tell me about this graph. What's the increase like? As pH drops, what's it like? Exponential. Yeah, we call it exponential. It goes along, and bugger me, it goes up really quick. Okay? See? Now, I want you to remember that because when you do your soil test and you're monitoring your pH and it's like, oh, it's 4 point, or maybe it's 5.2, and next time you look at it, it's 5. Just remember those small point increment decreases are actually potentially really large increases in aluminium. Seen? Righto? Especially when you get down this end, because it's exponential. So a little step on the x-axis gets you big steps up here. One last point I want you to take out of this graph. What else do you see? How precise is it? Yeah, it's a big variation, isn't it? There's a scatter. There's a scatter through here, see? So you could be at pH, let's call it, what, 4.3? At 4.3, you could have a soil that has maybe 4% aluminium, or you could have 76% aluminium. So what does that mean to you? Yep, that's the reality. That's what the data says. There's this big variation at a given pH, especially in acid soils, really acid soils. You can get a big variation. What does that mean to you as a manager, though? Just measuring pH doesn't tell you everything you need to know. Okay? So measuring pH is good, but we actually need to know this. Okay? And to get that from you're probably already getting it anyway. It's measuring the cation exchange capacity and how much aluminium's actually in the soil on those exchange sites. How many chairs are in the room and how many have got aluminium on them. Yep. Rightio. Now, the consequence of this aluminium, what it does. The big thing it does is it decreases root growth. It actually gets into the root and stops the cells expanding, which would give you root length growth. Okay, so to show you an example of that, here's, this is lucerne in the same paddock down near Mangaplar. We're not far from Wagga. And on the left, this had been lined, and on the right is a part where the line didn't go on. We use dig sticks, which are just metal tubes with a slot cut in them that you can bang in the ground and pull up cores of soil. We hit them up with a pH indicator. They change colours at different pHs. You can read that off a card that gives you an estimate of pH measured in water, which is different to calcium chloride. You always end up with a higher number this way. So basically yellows are really acid, the purples are around pH 7 or so, and the greens around pH 6, which are good. You think about that graph I just showed you, above 5.5 there's no aluminium. Okay, so this thing at pH 4, there's potentially lots of aluminium there. What that does to the plant, what do you see? Same plant, same paddock, different pH profiles because this has had lime and this hasn't. What do you see in that picture? Yep, so meaning that they don't go very far. Seen? What else do you notice about these roots? Fewer of them, they're short and they're stubby. Got it? Yep. So think about that in the field. If you're a plant and you've got short stubby roots, what does that mean to you in terms of your growth? Yep, you are limited to nutrient uptake from not all the soil, from just that bit where the roots are. Okay, so you're effectively, even though this is growing in a paddock, this is growing in about a 6 centimetre pot, because that's how far the roots are growing. So it can't get any of the nutrients that are down here. What else can't it get from down there that it would want? Water, righto? And then throw on top of that, if you're managing this land to improve it over time by getting more organic matter into the soil, more roots in there to give you better structural stability, you're not getting that here. Below that. With me? Okay, so that's a big consequence. The other thing is that's a legume. You have got it in the system because you want to fix nitrogen. There is not a nodule on this. So you need nodules on your legumes to fix nitrogen and put nitrogen into the soil from the atmosphere. I'm telling you, there was none here. So short stubby roots makes it really hard for the rhizobium to get into the plant to create those nodules. And also the acidity, the rhizobia don't like that. So they actually die out quick as well.
Is the lack of nodules related to the roots or the aluminium?
The aluminium's stopping the root growth,
yeah.
That stops the rhizobia getting in, but the acid's also killing the rhizobia.
Yeah.
So two whammies.
Yeah.
Yep. Over here, lined, got rid of the aluminium, roots can grow, higher pH, the rhizobia go, yep, I can survive here, will infect the plant, create nodules, so there's nodules all through this thing, and now you've got a legume that's actually fixing nitrogen. Now, those two things in the field, they looked sick. They looked like sick plants. They had a few things going wrong with them. Density wasn't very good. They were yellowing because of manganese toxicity, which is another problem with acidity. But this thing was not fixing nitrogen. So that's a system failure. You've got a legume that doesn't fix nitrogen is just a funky looking grass, right? So you've got it there, but it's not doing what you want it to do, and you've got no way of knowing it's not doing what you want it to do, unless you dug it up and had a look for nodules. Okay? That's a big deal, because if you're not getting that nitrogen from the legume, you'll be paying for it out of a truck. Now, I spoke to you about aluminium taking up all the seats. If aluminium's taking up all the seats, there's no room for the good nutrients that you need, like calcium, potassium, magnesium. So if they can't get retained in the soil, because there's no chairs spare, because aluminium's taken up, the good nutrients can leach down. And so it's not uncommon to measure in the top soil of an acid soil, very low pH, very high aluminium percentage, and because of that aluminium, this topsoil doesn't have enough calcium, doesn't have enough magnesium, doesn't have enough potassium. And so you'll see that in the soil test result, and depending on the calibre of your agronomist, they might turn around and say, put heaps of fertiliser on to overcome your problem, which are deficiencies and all those things, or they might diagnose it as an acidity problem, which you can then address by liming, getting roots to grow down to where the calcium, magnesium, potassium has moved to. Got me? When that plant takes up those nutrients, where does it go? Up into the plant material, gets eaten by the grazing livestock, goes through them back out onto the topsoil, and you've got your nutrients brought back up to where you need them to be. The cycle. Okay, so that's a big deal. The other thing with acidity and that aluminium is phosphate, a really important nutrient to you, will get bound to that aluminium. And if it's bound to the aluminium, that phosphate's not available to the plants. So you paid for it, you spread it out on your paddock, and now because you've got acidity with high aluminium, a lot of that P that you just paid for and spread is bound up and not available to plants. Take away the acidity, take away the aluminium, more of that P that you applied gets into the plant and you make money out of it. So there's an efficiency there. Acid soils just isn't just about increasing pH, because plants like a high pH. It benefits lots of things. One of the things that we've found also in getting around talking to people, and we see it ourselves, when you grow a plant in an acid soil, it is stressed. Okay, so it's under the pump from the get-go because it's a hostile system. And that makes the plant, which is stressed, much more susceptible to disease and pest attack. Okay, so we've seen examples, and this was wedge-tail wheat, grazing wheat, and on this side, that's a healthy root system from a good patch of growth, where we put the dig stick in and it was actually nice and green, so it wasn't acid. Around it, there were really bad patches, and it was acid, this yellow colour, and this was actually caused by rhizoctonia, so a disease of the plant. And the rhizoctonia occurred wherever there was acidity. So you had a sick plant that then got attacked by the disease. We've seen it with diseases, and we've seen it with pests. So the stress makes the plant more susceptible to attack. And again, calibre of your agronomist or your advisor, you see the aphid impacts, you could spray them, but they're there because the plant's stressed because it's acid. Now, one of the take-home messages I want you to have, agriculture is an acidifying business. So, doesn't matter what your belief is in what you're trying to achieve, the fact that you are agricultural producers, you are acidifying your system. And how that works is basically because of how plants grow. Plant, root system, green stuff on top. As a plant grows, it takes nutrients up through the roots. The consequence of that is, as it takes those nutrients up, it actually excretes acid into the soil to balance the charge inside the plant. Now the plant material, if I'm that plant material and I have neutral pH, I'm not acid, I'm not alkali, I'm neutral, and I excrete acid into the soil, right? I was neutral and I've excreted acid. What does that make me now? Alkaline. Okay? So as a plant grows, it takes up nutrients, excretes acid into the soil, and the plant material itself is alkaline. That's how it works. Doesn't matter what plant it is, that's how it works. So the soil becomes acid, the plant material becomes alkaline. Now, in a natural cycle, that plant material dies, the alkali goes back into the soil, neutralises the acid, cycle's complete, process goes again next time plant grows. With me? However, in agriculture, you are all about product removal. We utilise this. We take grain away, we cut it, make hay out of it, we put it through an animal, turn it into meat or fibre. So in agriculture, we remove the product. And therefore, in the cycle, all we have is the plant growing, putting acid in, and the alkaline material we export and make money out of it. Now, I'm not saying don't do that, because that's how you make money. Do that. In fact, the better you are at farming, the more of that you do. So the better you are, the more productive you are, the greater your rate of acidity or acidification. So a consequence of that is we have to put alkali back into the soil. Otherwise, we're just mining it into a more acid state. We have a tendency to use nitrogen to make the cycle go faster, to get more growth. be it from urea, ammonium-based fertiliser, DAP or MAP, or even legumes, it doesn't matter. You put that stuff in, you grow more alkali, more plant material, you export more alkali, you acidify the soil faster. Okay, so I want you to be aware that is a consequence of agriculture. And we can't just exist thinking that doesn't matter, I don't want to worry about it, because it's happening every year it happens. And it does catch up with you.
So this is the next step. One of the components of the project that we had with the NLP project with grasslands and Holbrook was looking at setting up monitoring sites to look at how the soils were acidifying over time. So when I'm long gone, there'll be still sites that have got GPS coordinates and good soil data, so we can go back and check and look at the rate of acidification. But we just so happened to find at one of those sites there was a good comparison of a undisturbed native pasture in a large cemetery area, not near trees or anything, and the pH down the profile was pretty well ideal. So pH, calcium chloride above 5.5, could grow almost anything there, so pretty good. So the 40 metres away was paddock that had been cleared in and had been farmed since about the 1930s, and it's still yielding 7 tonnes of wheat, almost 3 tonnes of canola, lupins, and it grows hay. So it's a really quite a fertile soil, cation exchange capacity of 10. So it's that really nice red-brown soil sort of around this area, sort of south towards Canowindra. And there are no symptoms of any soil acidity problems at all. Everything's going smoothly. It has had, as you can see, a history of lime application 3 times in the last, it's almost 80 years of farm management, 94, 2003 and 2018, so 7.5 tonnes in its life. And this is the pH profile. And what we have found in a lot of the survey work we've done, particularly in the cropping areas where they really grabbed hold of the liming messages that came out of a lot of work that was done in the 80s to 2000s, there's a message that's come out that we need to lime if you want to grow lucerne and canola. In the early days we were talking about incorporating the lime, but now we're just top dressing. And as you can see there, the pH in the top 5 centimetres is quite elevated, and then it drops down quite significantly. So certainly from the work that we've done, it shows that the liming programs at the moment are keeping the pH in that very top layer where you would like it to be, but further down the profile, it's being acidified. So what we're doing at the moment is basing our decisions for liming on 0 to 10 centimetre soil samples. And sometimes 10 to 20, but most of the time it's just 0 to 10s. And that's based on that graph that Jason spoke about before. And what we're doing is you're looking at applying lime when the pH is dropping to about 4.8, when the aluminium levels start to usually increase above 5%. So a 0 to 10 centimetre soil sample, when the pH is about 4.8, you're likely to be seeing in most soils an aluminium level of about 5%. And if you're wanting to grow canola, pulses, barley, lucerne, then that's where you start to be concerned about maybe affecting the growth. So, and the strategy, the liming strategy, has to be raise the pH to above 5 to get rid of the aluminium. And so what we're doing is we're operating in this range. The soil in that 0 to 10 is fluctuating between 4.8 and 5.2. And what's happening there, as you can see, you're going to have a lot of cases the pH may be below 5, but then as it drops back, then your aluminium's likely to be increasing up to levels that might be toxic for some of those species. You're not going to be seeing obvious symptoms of toxicity, but the plant's going to be stressed, what we call subclinical symptoms. So you're not going to be able to pick up that pruning of the root systems until you start to see symptoms of top growth, which is symptoms in the top growth, which is when you're going to actually have a really stressed plant. So when you're operating in that range, there's a fair chance that you would be, that the productivity would be compromised.
Just before you go on, Helen. So,
Sorry?
well, that's right. The bit I struggle with is this. It's a legacy of when liming first became a practice in the 80s and 90s, when it was, the value of land was relatively small compared to the cost of liming. Okay, whereas now the value of land's huge and the cost of liming is about the same. And so back then, you couldn't aim for pHs up here because you'd be spending more than the value of the land to do it. Okay, and so what that meant was, this was where you managed in between here. Acidify until it hurts, lime to make the hurt go away. Farm until it hurts again, lime to make the hurt go away. And the bit I struggle with that now is, what that means is we keep liming that using this same practice. We are farming so we feel the pain, and then putting the lime so the pain goes away, which is stupid. Why would you do that? Why think of another part of your life where you'd be willing to accept pain and suffering just so you can see it go away again? Like, surely you'd operate up here where you never have to feel the pain, right?
With that range, that sort of 4.8 to 5.2, in pasture systems we found that that's more likely, the trigger to lime is more likely to be about 4.5 when your lucerne starts to drop out of your pasture or you're having issues.
When you work it out over the 24 years they put that lime on, 7,500 kilos, it was only $20 a hectare spread per year. It's stuff all.
Yeah.
But that used to be one chemical. That's basically nowadays it's one Roundup application.
Yeah.
1 litre a hectare of Roundup spray, yeah. Just 1 litre.
Right, so how much lime to put on to get to that point is basically, some people have rules of thumb, but a lot of that comes from some research that was done in the 80s, largely. And this is a table that's in the DPI AgFact or Prime Fact. And it basically shows different cation exchange capacities and then how much lime do you have to put on to get from a starting point of 4 or 4.3 or 4.7 up to 5.2. Why is 5.2 important? Because it's more than 4.8. Above that, the aluminium disappears, yeah? So this is getting up to a point where aluminium disappears to give you a few years before the hurt starts again. Okay, and so down here, the numbers are higher than up here because you've got much more acidity because you're at a much lower pH. Okay, now, and so that's where a lot of the, how much lime do I need to put on based on my soil test result, right? Notice this column, this is the extra bit of lime. If you're already at 5.2, you do whatever you have to do here to get to 5.2. This is the extra bit of lime to get to 5.5, which, as you said, after 5.5 or at 5.5, there is no aluminium at all. Now, an issue is, all of that work that led, all the trials that led to the formation of that table involved putting high quality lime on the soil and rotary hoeing it into 10 centimetres. Okay, and that's how you get that amount of lime on that soil to get that pH change. Who does that? Nobody does that, right? And so to use that table to calculate this is how much lime I'm going to put on to get this pH change, unless you're mixing in with rotary hoe, you're not going to get that result. And so it kind of sets us up to fail in a way. It uses high quality lime, and not everyone does that. Around here you probably would because it's close, but depends where you are. And then all of that table targets this short-term, what I call a short-term response, in that little zone of making the hurt go away, feel the hurt again. This table, all of it, or 75% of it, just gets you to pH 5.2. Feeling the hurt, make the hurt go away. The highest point is 5.5. There's no more data beyond that. We don't know how much lime to put on to get over 5.5. There's no data on that in this table. So the outcome of using those rates.
Well, this is a recipe came out of that work in the 80s to 2000s, which most of you would have heard because it's national, doesn't matter what your soil type's like. It's 2.5 tonnes of lime every 10 years or so, incorporated. So again, we did some surveys, and this was surveys of paddocks that were specifically chosen because they were good quality paddocks and people wanted to grow pulses on them. And we split the samples between ones that had been limed in the last 5 years versus those that hadn't had lime in the last 5 years, or more than hadn't had it for more than 5 years. And these are the two graphs that we've got. This one here, limed recently. This one here, not limed in the last 5 years. And what do you see there? The lime's working up to about 7.5 centimetres. You're getting an increase in pH to that. But once you get down to 10 to 15 centimetres, the lime is obviously it's not going down there. And we did some comparisons of paddocks or of surveys from the past to looking at this data, and we found that while the pHs in this sort of layer, the 0 to 5 and 5 to 10, were sort of the same, that it was becoming more acid down in that 10 to 15 centimetres. So what we're doing with the current practices, putting the lime in the top at rates probably not high enough to be getting the lime to move down to the subsoil, to the subsurface layers, and this layer here, it's acidifying. So in the old work they used to talk about this pH stratification, different pH at different levels down the profile, and they used to talk about 5 to 10 being the most acid layer. Now we're talking about an acid layer, an acid throttle, at 5 to 15.
Before you go on.
Yes.
So Helen mentioned that the rule of thumb there of 2.5 tonnes to the hectare every 10 years, because that's all the work that was done in the 80s and 90s, that's roughly how acidifying the farming systems were based on the productivity of the day. Now, for those of you old enough in the room that have been farming long enough, think about your productivity in the 80s and 90s compared to now, right? Is it the same? No, we're more now, aren't we? Righto? So we are much more productive now for a whole range of different reasons, so our rate of acidification is higher now. And I spent a lot of time dealing with cropping areas, our yields are higher. We have dual purpose crops that we graze and then harvest, two different types of acidifying functions.
And put nitrogen on.
And put heaps of nitrogen on. So we are winding that sucker up real tight, getting a lot of productivity out of it, which is great, but we are much more acidifying than we were in the 80s and 90s. And so if we keep putting on lime to address the productivity that we had in the 80s and 90s, we're always going to lose. And the consequence of that is that when you do that, you spend the money, but you're not fixing the problem. Okay, you think you've fixed the problem, but it's still there. And that used to keep me awake at night. I'm a little bit more comfortable with it now, but that, to me, that's worse than not doing anything. When you think you've fixed a problem and you haven't, you're in a bad situation because you think that you can do all these things that you can't.
Any comments? That acidification rate of roughly 2.5 tonnes every 10 years was 250 kilos of lime per year you should be applying, which we suggest is probably not enough. So we're just tinkering around the edges, and it's feeling good because we're doing soil sampling at 0 to 10 centimetres, that if you've got a reasonable liming program, you're probably maintaining your pH around 5, or in that, certainly in that 4.8 to 5 plus zone.
So if this was your soil, it came back from the lab, and it came back at 4.6 in the 0 to 10, what would you be thinking?
Would you lime?
Yeah, it'd be on your list of things to do today, wouldn't it? Right? But if it came back at 5.3, you would think, job's right. Let's go and sow whatever it is I want, because I don't have aluminium in there, I don't have an acid soil anymore. And yet, look at the reality. You've still got this nasty bit. This is pH of like 4, 4.5, 4.6. And remember the aluminium graph? It could be horrendous at that pH. And you don't know, you think it's fixed. That's what I'm talking about.
Now, in 2015, I was on a geodesy project that was looking at pulses and why pulses weren't growing on acid soils in the high rainfall zone. And I was very grateful that a farmer down at Holbrook sowed some favour beans. And before he sowed the favour beans, he had applied 2 tonnes of lime in 2010 and top dressed it. Applied another 2 tonnes in 2015, used a speed tiller to incorporate it. Did a 0 to 10 soil test and it came back at 5.2. That's okay to sow favour beans because there was also no aluminium at 5.2. Then 6 weeks after the favour beans came up, they were looking okay, then they went yellow. And he rang me and he said, I don't think the inoculant worked. And that's very obvious. That's canola in the background. It's already had a dose of nitrogen on it. This is favour beans in September. And obviously they weren't nodulating. But I dug up some plant roots. And this is what they look like. And favour beans should have, the root, this is 5 centimetre interval. The comparison of areas of the paddock that were okay, the roots were right down to 15 centimetres by the time they were that age. And you can see here, we've got those stubby roots. We've got no root hairs. No root hairs means no nodules. And you can see the taproot on some of them is actually curling back up. So when it just didn't get any root system below 5 centimetres. No nitrogen, yielded a tonne with a dose of 50 kgs of N on top of it. So that canola in the background, it yielded 2.3 tonnes. But that's what the root system on the canola looked like. And a canola plant, particularly in that environment, 2015 was a dry season, it should have been tapping moisture from down a metre, but it's almost like growing hydroponics. So, any comments, questions? Do you see root systems like that? The story, they talk about J-rooting. What do you do with J-rooting? You deep root it. That, if you did a soil test, then it's pretty obvious that it's the pH that's causing that J-rooting. It's not a compaction issue. Favour beans are the most suitable pulse to be growing on those acid soils if you can fix the aluminium because they're quite tolerant to waterlogging. Once you fix the soil acidity, the favour beans, we got a tonne from that, but they should have been yielding up around 3 tonnes. 3 tonnes is an ameliorated version of this soil. 5 tonnes is what you'd be looking at on an ideal soil with a deeper root system. And the wheat here would yield 6 tonnes, but anybody who's familiar with yield profit, the yield profit model, which talks about maximising the water use that's available to you, to the plant, it should have been, the wheat should yield 10 tonnes. If canola's yielding 2.3, on that soil it should be yielding 5 tonnes. So it's the acidity that's actually probably in this country on the cropping side is probably limiting production by at least 50%. We haven't got enough information to talk about what's doing to the pastures, but one of the studies we did suggests that probably we're looking at around about 30%. But John's going to talk about that.
So that example of the favour beans, the farmer was in trouble there because the soil sampling that he didn't identify the problem. Okay, that 10 centimetre sampling didn't pick up that he had an acid layer that ultimately hurt him. And so that led us to the question, well, how do we do it? What's the best way to identify whether we've got these subsurface layers of acidity? And so what I'm going to show you is some graphs here. We've got pH along this x-axis in our 10 centimetre increment. So what we did is we sampled a bunch of soil in 2.5 centimetre increments, right, because we've got nothing else to do with our lives. So that's what we did. And then if we average those over 10 centimetres, that's effectively the number that you'd get back from the lab if you sent away a 0 to 10 soil sample. With me on that? So this x-axis, the data that's coming up, that's pinging on that, is the value that you'd get back from a soil test analysis if you sent it off to a lab, okay? The y-axis, what we have here is within that 10 centimetres, because we sampled in these 2.5 centimetre layers, we can actually say, rightio, what is the pH of the most acid 2.5 centimetre interval within that top 10 centimetres? And so that's what this y-axis is. So within the same soil, what is the pH value of the most acid bit of the first 10 centimetres? And I like to say, what would the plant see? What's the acidity that the plant would see? That's the y-axis. What's the acidity that the soil test tells you is the x-axis. So in the ideal world, our soil test would tell us what a plant sees. Got me? And if that's the case, and we lived in an ideal world, and you know we don't, the data would hit that line. The soil test value tells us what the plant sees. The soil test value tells us what the plant sees. So we sampled a bunch of soils, stuck it in, and that's what the data looked like. And you can see that hardly any of them touch this line. So what this says is that there are soils here that the soil test value says I've got a pH of 6, but the plant growing in that same soil would actually experience soil pH of, in this case, 4.5, 4.4. Yeah.
At some stage, in one of those.
In one of those layers. And here's the thing, if you're a plant growing down, you only have to hit that acid layer once. That's the damage, yeah? So you see how, and so these were probably lined. This is the top soil of the fade and bean crop, you know, it's lined, the top layer might have been high, really high, so it averages out to be a big number. But within it, you've got acidity in hertz. So this is saying to me that when you measure in 0 to 10, send off to lab, yes, you get a number, but the number doesn't actually tell you what a plant sees. There's a bad way of measuring soil to find acid layers.
And if you've got a liming history, a strong liming history that's top dressed, because that most of them are at the moment, no incorporation with minimum tillage, that is going to be more incorrect, your 0 to 10.
Yeah. And this is the false hope I talk about. You did something, you limed, you know you've done the right thing, problem should be solved, soil test says it's good, crop failure. Okay? So we then said, well, rightio, current system's buggered, so that doesn't work, so what does work? And so we ran a bunch of different ways of measuring in different increments, and what we found is, if I show you now doing exactly the same thing, but now looking at 5 centimetre increments, 0 to 5 and 5 to 10, right? Exactly the same. So this is what the soil test would come back if you sampled in 5 centimetre increments, and this is what the plant actually sees. For the 0 to 5, it looks like that. So we are much better, much closer to this dotted line. Not exactly on it, but much better. And then the 5 to 10 is right there as well. So this is the data, this is the evidence to say if you measure in 5 centimetre increments, what the soil test value says is much closer to what the plant will see. So 5 centimetre increments actually gets you what you want to know. It will identify if you've got an acid layer there that could limit what you're growing.
Question, why isn't that black line further to the left? Because all that's telling me now, I know the dots are on the lower end, but it's still telling me that the 5 to 10 is more acid because I'm now most of them less than 5. That's right, I've got it.
Yeah, so we're much closer to the number.
Quite often people ask us to come and talk, and I ask, have you got any local soil data? Because we're just relying on the stuff that we've got, which is quite extensive, but there's nothing like having your local soil data. And people say, no, nobody has been prepared, nobody's really interested in the 5 centimetre intervals, we've got 0 to 10. Well, a 0 to 10 tells you absolutely nothing about how acid the soil is or the depth of the pH, of the acidity. And if you're trying to, we'll go into this a little bit more later, but if you're trying to work out how aggressive your liming program needs to be to fix this subsurface acidity problem, you need to know how acid it is and how deep that acid layer is. It's not only about how much lime you put on, how aggressive you are in incorporating or whatever, but also gives you a bit of an indication of the success you're going to have with the different species.
And that information is everything to you as a manager. This example is fantastic for that. This line, whilst it's average, this line, when I look at that, I see this is the acidity, but importantly, it's at this depth, which isn't that deep. You can do something about that. Okay? You can cultivate to that depth. If you can get lime in there, you can bring all of that up. If you bring all of that up over here to that point, and to the right of that, you can grow whatever you like there. And it's all within reach. If this continued down like that, we'd be having a different conversation. Whatever change you make up here is only ever going to change up here, and you've still got acidity lower down, which would mean you'd have to factor that into what you expect your pastures to grow or your crops to grow on that soil, because you know it's still got acid at depth.
So how deep do we have to go?
We'll cover that a little bit later, I think, won't we?
We can, but in the absence of knowing anything, we're saying 20 centimetres in 5 centimetre increments. And here's the thing, because like some people say, oh, it's going to cost crap loads. How many of you get soil tests done? Yep. How much does it cost to get a soil test done? Yeah, how much? Yep, okay. So they're the sort of numbers that get thrown around. And I just said 0 to 20, I'm going to get 4 of them done. And people go, geez, that's going to cost me heaps. The soil samples that you send away and you get soil tests back, you get a page that's got all this data on it. Do you use every single line of data?
What are you
No?
using?
What do you use? What do you look at?
pH and phosphorus?
Yeah, Coal P, like pH, maybe cation, like phosphate or, potassium or magnesium, maybe, right? So I say, don't measure everything if you're not going to use that data. Measure the stuff that you actually look at, right? And if you do that, for 4 layers, 0 to 5, 5 to 10, 10 to 15, 15 to 20, and you measure pH, cation exchange capacity with aluminium, and coal wall P, that's less than $30 a layer. That's $120 for the whole site. You actually spent less money than you used to, and you're just getting the bits that you actually use. You with me? So don't pay for stuff, and like, go figure, people that make money out of selling it, they're not going to tell you don't do that, right? So if you...
The big issue there is the time involved in doing it. What we're saying is that you should do it a baseline, just to know where you're working from. And ideally, you should check every couple of years to see if it's working, but at least start with a baseline so you know what to do.
And so it's not every year, but if you were going to go, if you knew you were going to sow or you wanted to sow something that is sensitive to acidity, or you're worried about your acidity, or you have limed and you're wondering what the impact of that was, that's when you pull out these 5 centimetre intervals and have a look. Because I'm telling you, the guy that grew the faba beans, if he'd done that, guess what, he wouldn't have grown in that paddock.
And
right?
actually with that, we surveyed a fair proportion of those paddocks. There were 13% of soils that were okay for pulses right down the profile. And there were more than 50% where they would have suffered a yield disadvantage because of that stratified pH.
And so, question is, well, how do we get lime deeper? How do we get rid of this acidity deeper down? Helen showed you the graph that says our current practice mucks around changing pH at the surface, but we've still got this acidity down sort of 10, 15 centimetres. Well, how do we do about that?
How quickly does it move?
That's a good question.
We've got stuff.
We'll get to that, and if you're not happy, let me know. So, one of the things you can do is rely on line movement, and how quickly does it do that is a fair question. I'm going to show you another bit of data here. So, to work this out, researchers back in the 80s did some work. What they did, they had 3 lime treatments: a control of doing nothing, adding 2 tonnes, which was roughly get your pH up to 5 to get rid of the aluminium, and then 8 tonnes, which you would know is a crap load of lime, right? They put those treatments out on the field and they rotored them in to what they thought was 10 centimetres, mixed it in. They put subclover in, and they came back 5 years later and measured in 2 centimetre increments. Okay? So, 5 years after liming, this is the soil pH and calcium chloride. This is depth down to 18 centimetres. There's an eye that appears roughly around about 8, which is the depth of incorporation. Right, the control that had nothing. This is what it looked like. And you'd identify that curve as the same curve that we've been showing you this afternoon. Yeah, this stratified layer, acid zone here. So this was initially mixed, and after 5 years, we've got this going on. It's higher at the top with no lime application. Why would it be higher at the top? Yeah, all the plant material, subclover, decaying leaf material hits the surface. That's an alkali source. The pH goes up.
So was this trial grazed or after?
It had just been under subclover pasture. So,
There's no way.
yeah, grass,
Oh, yeah.
starting with grass. So it's
Yeah.
back to non-research.
But over, not like each plot wasn't fenced. It was just, yeah. And so acidity is formed here, but alkali return goes to the surface. So that's your stratified pH. We understand why that occurs, but it's still acid. Where 2 tonnes went on, they increased the pH to the depth of incorporation. Okay, and on average, that on average is about here. So the 2 tonnes got close to 5 to get rid of aluminium. So that worked. However, when you're liming at that rate to get rid of the aluminium, the lime, the alkali bit, which is the opposite to acid, is alkali, it can't move because it gets used, it gets consumed where it was put. So you've got no effect below that. So this is that mindset of liming to get away from the hurt, get away from the aluminium. It only gets rid of aluminium where you could put the lime, the depth of incorporation. Now, when they put on 8 tonnes, this is the lime. And you can see down here, below the depth of incorporation, they got big pH changes down to about 12 centimetres. Okay, so they got an extra 4 centimetres of pH increase after 5 years. So that answers your question a little bit. See? Rightio? Now, here's the thing. When this work was done, which was in the 80s, the message that was extended from this work was if you want the lime to move down, you have to put on a crap load of lime. And at that time, that lime would have been the value of the land. Rightio? So no one's going to do that. So the message was, if you want lime to move down, you have to put on really high rates of lime. And everyone walked away from that and carried on doing exactly what we've been doing for the last 30 years. The problem is, when you read that paper, what it actually says is, if you want the lime to move, the pH has to be over 5.5.
The 0 to 10.
0 to 10. Now, it just happened to be that this soil, to get it to do that, and the average of that is about here, to get this soil to over pH 5.5 in the 0 to 10, you had to put on 8 tonnes because initially it was about pH 4.1. It was really, really acid. So if you want lime to move, you just have to keep the pH up over 5.5. And if your starting point is 5, you don't need to put on much lime at all to do that, to pull that off. But if you wait and do nothing for quite some time, the soil gets more and more acidic, and to get it up over 5.5, then you need to put on a lot of lime.
It's getting more acidic and getting more acidic to depth.
Deeper. Now, so that we knew. in the late 80s. Okay? But the consequence of it, we didn't really understand. I'm going to show you data now, and the graphs change a little bit. Now we've got pH here, acid down the bottom, but the x-axis is years of the trial. So I'm going to show you long-term trial data that goes for like 18 years. Okay? And it's from a trial that was done just east of Wagga at a place called Book. Now, I'm going to show you graphs from the 0 to 10 because at the time they didn't sample in 5 centimetre intervals because we weren't telling what to do, because if you're doing that now you would. And they measured in the 10 to 20. Now, using that standard practice of liming so you just make the aluminium go away, you end up with a line like this. I've got an acid soil in the 0 to 10 of pH 4.5, is acid, I need to put lime on. You put lime on to get up over 5 to make the aluminium go away, we've won. Then you do agriculture to it and you acidify the soil until it gets to about 4.8. Then you put lime on to make it go up over 5, up to around 5.2-ish. You let it acidify, re-lime. So this becomes what I call a sawtooth of lime maintenance. You with me on that? Rightio. And that's standard practice, right? That's what people do. This is profitable, right? That you see response and you make money and that's great. However, when you do that, exactly what Helen showed you with that graph, you only ever muck around in that 0 to 10, probably 0 to 5 centimetre layer. In the 10 to 20 layer, what actually happens is the pH continues to decrease because none of that lime is getting down here because it gets consumed. Okay, we never got the pH up over 5.5 to make the excess lime move down. And so our 0 to 10, which wasn't flash hot at 4.2, actually acidifies down to 4, where I told you at the start of the talk, you can throw acid at it, it just dissolves the soil. Okay? So that's bad, right? Yes, we're making money, but our long-term problem, which is this nasty acid layer in the 10 to 20, we haven't touched it. Compare that, and this is what the data shows, if you change your program, instead of liming to make the hurt go away, let's lime to get up over 5.5. Because up over 5.5, we get the lime effect moving down. So here's what that would look like. A liming event to get the pH up over 5.5, not to 5.5, over 5.5, because you need excess outflow. Up close to 6, let agriculture acidify. When it hits 5.5, re-lime, get it up again, let agriculture acidify. So you've still got the same sawtooth maintenance, it's just occurring higher up the graph. With me? What's the difference in reality between those two things if you were going to do that? If you were doing this and you went to do this, what's the change you're going to make? Yep, so a higher rate of lime at the start is the difference, and then probably lower amounts of lime here. Now I can tell you on this trial, that was 3.7 tonnes of lime. Now, you're with me on my terminology, is that a crap load of lime? No, it's a bit, right? It's more than most people do, but it's not get out of town, don't ever come here again, I don't want to hear your message, right? So it's doable. And I like to think of it this way, this is 3.7 to get up here, this was 2.5. So the difference is 1.2. And 1.2 is nothing.
Is this all still surface applied?
Good question. Really good question. This was incorporated. Everything after was surface applied. Righto? So they incorporated in and established the pasture and then top dressed only. Yep, you don't need to incorporate it because it's going to move, is the theory. Did it move? Is the question.
What's CEC out of interest?
Come back to you. This is what happened. This is what happened in the 10 to 20. That change got us an increase in the 10 to 20 over 18 years that got the pH up to 5. So this is a 0.9 of a pH unit increase over 18 years to pH 5. Now, for those of you playing at home, what does that tell you? If this is at 5, what does that tell you about this soil at 10 to 20? What doesn't it have in it? No aluminium. So this soil, which used to be horrendous, now has absolutely no acid barrier for that deep.
And there was obviously an extra application in that as well.
It's
No, that's your drawing.
that's my drawing, right? It's
Well, taken that as.
it's notional. It's notional because that paper's like really complicated, right? So I'm backing what I've got here, but what I'm saying is why it's like that is because I wanted someone to ask a question about it. Because what you do here, think about the productivity of the system. What's the productivity like over here compared to here? It's going to be more. So you're making more, you're producing more. So your rate of acidification is more, so you might need to actually reline. But here's the thing, this reline up here, when you're at this pH range, a little bit of lime gets you more of a change. These rates of lime were around anywhere between 0.8 and 1.3 tonnes of lime. That was the reline maintenance per hectare. Yeah. So it was doable, right? The difference is I've got to keep the pH up over 5.5. The cost of that is really borne once at the start, and it's not a stupid quantity of lime necessarily compared to what you were going to do anyway, which wouldn't get you a long-term benefit.
If you're growing more vigorous plants on the top that should, in theory, grow deeper roots, and if lime's getting deep, your roots should go deeper. So by having deeper roots, does that help take the lime down further again?
Yeah, so I know what you mean, because you've got more pores and stuff.
Yeah.
And so like I get that. The other thing working away that is you've got more roots, so it's taking up more nutrients. Yep. So the question there is, well, let's find out what happens with research.
Yeah.
So over 18 years, we've still got a pH going up here.
Yeah.
So we're still a net positive, right?
Yeah, and that's from lime application, not from roots.
We can't separate that with the data. Yeah. So I understand your question. We've got long-term trials in the ground, which Helen's talking about in a minute, and we can see the effect. We won't necessarily be able to say how much was due to roots and how much was just due to lime movement.
Everybody knows it all together it all works.
Yeah.
So is there any other medium other than lime to increase the pH, such as liquids, or is there any?
Yeah, there is, and we've toured around a little bit with that, and I will stand here and say lime's still the most cost-effective thing to use. There are other products that you can get really excited about, depending on the quality of the salesperson. But
And the depth of your pocket.
yeah, lime, like I know what I'd be doing.
So the other thing that, one of the myths that carried over from some of the discussion from years ago was that the most acidifying system we could have would be subclover pastures. The subclovers, sub and super, were actually the reason for acidifying. And this site had a comparison of annual pastures and perennial pastures. And the idea was that the perennial pastures would suck up the nitrogen to prevent that deep acidification at depth. And so that the perennial pastures would not have the acidification rate of the annual subclover pastures. What this found was, because the productivity was increased in those perennial pastures, the acidification rate was exactly the same. So that myth about subclover pastures being more acidifying, if you've got productive perennial pastures, they can be just as acidifying.
So the same way of saying that, but from the different direction, is I know when I was in uni, we were taught perennial pastures take up nitrate from deeper. And so therefore, they are the solution to acidity. Grow perennial pastures, take up the leached nitrate, and you'll slow acidification rates. And it's just not true. And I can explain that in more detail if you want, but the data shows it's not true. When you actually engage thought about how plants work, it doesn't work either. Yep.
I don't know if you've done the work, but what is the difference in grazing management then between the grass hayers and the grass hoppers? One that might leave 30% of litter every graze, and the other one that's there taking leaving no litter.
I haven't done the work, so straight up, I haven't done that. But that litter, you've seen, and here's the thing, right? That comment I made about nitrate and perennials and being taught that that was the solution. It was because the people that came up with that went, right, here's the soil, think of it like a bucket, and you've put nitrogen in and it's acidifying, and you've taken out a grazing or cut hay or whatever, and that's alkali removing, balance it all up, I've got a net effect of it's acid or not. You with me? But it was like a bucket. And so to answer your question, the grazing management, I've got leaf material, which is alkali, still in the paddock, or it's gone into an animal and maybe moved, right? So you've lost alkali. So if you're thinking it as a bucket, which one's going to be more acidic? Which one? Yeah, the one that removes everything, right? But here's the thing. Soils aren't buckets, they're layers. Layers, like they're built up of layers, and all the processes occur in layers. And so if you've got roots down there taking up nutrients, where's the acidity due to that nutrient uptake? Where does that hit? Wherever it got taken up, wherever the roots are, yeah? Where's the alkali get returned? On the very surface. And so as a net effect, I've got no acidity. Yeah, you have. It's in this little bit here that is not attached to the surface. You with me? And that's a big problem. Because that, thinking of soils as a bucket, allowed us to think we could farm this way and not have an acidity problem. Where in actual fact, what we were doing was creating acid layers deeper down. And we didn't know it because we never sampled looking for them. So does that answer your question, kind of?
So if you have the facilities to work on 2.5 tonne and you can incorporate to 20 centimetres, would you?
Yep, so again, so I'm not dodging your question. I'm hoping that our presentation answers it, and if you're not happy, let me know, because but we're answering that question with our research that Helen's about to talk about.
I might actually.
Well, you can.
So one of the, just to follow on from your question, heavy grazing and erosion would be the most acidifying because you're losing that top layer of higher pH soil if you've got erosion.
Yeah, exponential.
Yeah.
But that's not, it's erosion.
It's one of the other, I mean, from when you're talking about the grazing management side of things, that it's important, that ground cover is important. Maybe not as much for the process as protecting it from erosion.
When you're grazing, the sheep go and take it to sheep camps and the cattle put it under a tree or in a creek, yep. So it gets taken away.
Yep, that's true. So
unless you're doing heavy short term
yep.
grazing, when you spread it over the whole paddock.
Yeah, so you nutrient export, yep, so that happens. And so underneath, where the sheep camp, you'll have a high pH because they're returning more organic material.
A lot more
back to where it was.
So yeah. A lot more is going there than is going off in the wall or the leaf. You work it out when they flip every morning. Yeah.
Yeah. So you just remove all the trees and then you've got no camp.
Well, I camp on the northeastern corner of the paddock where the sun is early in the morning.
I know people have done postgraduate studies on exactly that for sheep camps. I did my PhD on urine patches, which is a party starter. But
have you ever done a test on holding cattle grazing property and holding sheep grazing? Like, wouldn't there be more return and better acidity?
Yeah.
In the
it doesn't
higher acidity levels in sheep grazing areas than cattle.
Doesn't, from my memory, it doesn't make much difference. You just got different.
Look over the notice fence, you've got all cattle, and there's always cattle.
Yeah.
And your sheep will flog your paddock out to nothing at times.
Yeah, in terms of nutrients.
There's cattle don't seem to do it.
Yeah, no, I've read stuff like that a while ago, but the animals are different. They're bigger, they eat more, and they poo more, and they wean more, but like, doesn't really matter. It's a DSE, if you like. You can neutralise, make an equivalence with DSE. I think your acidification rates would be ballpark similar for the carrying capacity.
So we might move on. This is some of the work that we've been doing, and a lot of what we talked about was the basis for this stuff that the trials that we've established more recently since 2019-20. So we had the NLP project with Grasslands and Holbrook Landcare that then developed into a bigger project, and we now have 18 sites across southeastern New South Wales. We've got replicated trial sites, big sites, so up to 2 hectares, and what we've got is either on established perennial pasture with just top dressing, and we've got standard treatments of nil lime, the liming to a target of 5.2, which is what traditionally has been done, and then going for this pH, maintaining pH above 5.5. And so the target pH that we're aiming for is close to about 6. We've also got another one, we've got a reference group of farmers and advisors on these projects, and they were looking at wanting to know, particularly for the perennial pastures, what about if we just looked at maintaining pH in the top 5 centimetres at 5.5? So less lime, but putting it on more regularly. So those were the treatments in the top dress trials, plus where we could, we incorporated the lime with various pieces of equipment. And then when we could do a deep incorporation, we added another treatment which we call once in a generation. So if you're going to lime, and if there's a risk in erosion from cultivation, and you're going to do it, well, do it deep and put in a decent amount of lime. So this was really pushing the boundaries. In the past, people would have said that if you're putting on more than 4 tonnes of lime, then you risk developing deficiency symptoms. We wanted to really push that to see if we could run into those issues. So this is what this is a site we've got at Brentford. This is yours, Jason?
Yeah. So just different implements, so offset, a speed tiller and a speed chisel, which is just like a speed tiller except it's got ripping tines on it as well. So we've done it like there's a Horse Tiger, a Great Plains tiller and a speed chisel. They're all the same type of machine, different colour, right? So different brands trying to achieve the same thing. We had with and without lime, and put it in the ground, came back, measured pH. This was the and pretty good soil. That's the starting point. That's what the no lime, that's what the pH looked like, and you can imagine that average would be about there somewhere. So it's maybe pH 4.8-ish on if you measure 0 to 10, but in actual fact you've got worse acidity there. Now, we put implements through without lime because how much of the effect is cultivation, how much is mixing. So we did it without adding lime, and that's what it looked like. Tell me what you see.
Same.
Yeah, more or less the same. Speed chisel had these sort of a little bit higher, and I suspect what happens is there's a bit more clay down here, and the tines actually ripped that up and threw it in here, and that's why it's a little bit higher, but probably not different really. Lime on the surface only, so spread on the surface but not incorporated, and the scenario there is, and I know people like this, we used to cultivate and we didn't, we went no-till and the farm's been better than ever, I'm never going to cultivate again, so they put lime on the surface. That's what happens. What do you see there? Yeah, we've increased the pH up here, where you identify we didn't have a problem anyway. Yep. And we've done nothing lower down there. So those people that put lime out and don't incorporate it, so all of these would have been, there's sowing as well, so mixed in by sowing as well. But this is, I put lime on, incorporated by sowing, job's right, carry on. Okay? They actually haven't done anything to where you're going to put a seed and expect roots to grow. With me? Now, next, offset, lime offset, so we've got the blue triangles. Speed chisel, speed tiller. Tell me what you see. What do you see? Same. So I take away from this, doesn't really matter what colour the machine is, it's not actually doing much different. Okay? Now, the other thing you see in this, we're not actually getting much effect down here at all. Our cultivation, this speed chisel thing, it went down to 25 centimetres. Okay, these other things incorporated down to about this far. And so here's a universal learning that I've taken from the work that we've done, and you see it in the literature. Whatever the depth of incorporation is not the depth of lime mixing. right? The fact that you got an implement down to that depth doesn't mean there's lime there. And it's in the literature. A lot of the lime's still actually in the surface, and there's more of it at the very surface and it tails down. You with me? Rightio? So our mixing is never as deep as we think and is never as good as we think. And the implement doesn't really matter too much from this piece of work. Now, I've spoken a lot at the start about aluminium. That's the aluminium. This site, the worst of it was about a bit over 15%, which would towel up a few species. Helen, help me out. Lucerne
bisag, barley, canola. Canola mightn't be showing symptoms, but bisag.
Yep.
Pulses, you shouldn't grow them.
And so,
Clover, nodulation.
So what do you see? You see for all that intervention, we still have an aluminium problem in all treatments except for that one.
That's still a problem.
But yeah,
You wouldn't be getting clinical symptoms, but the plants wouldn't be functioning properly.
Now, on that, so FarmLink look after this trial, and the guys running it, you say, oh, you know, how Grenfell, blah, blah, blah. There's nothing to see. Like, there's no treatment differences. What are we going to tell growers? There's no treatment difference agronomically above ground. Okay? We got this soil data. Look at that. My question is, why would you have agronomic difference? We've still got an acid layer. The plants are still trying to grow through that. Okay, so we actually haven't got a difference yet. Despite all that cultivation and cool machinery, we still haven't got the line to where the problem is after 1 year. So we've sampled again this year, but we haven't got the data back yet to show you. Okay?
Do you think it's going to change?
I think it'll move down. I'll show you why I think that in a tick. But it'll move down a little bit, but I think it's probably going to move down the same. I don't think implement's going to matter. Again, I don't think implement's going to matter. But this, when I saw this, I thought, well, maybe we need to do more passes of cultivation. Okay, so we've got trials now that we do a bit of that as well. Well, let's have a look at that, Harvo. So another trial, which is at Lyndhurst. And so same sort of treatments. Control current practice at 5.2, greater than 5.5, little and often, and the once in a generation. You're familiar with that. It's the same sort of treatment structure. Now, the data. So soil depth down to 30 centimetres. pH, as you see, there's one over here, there's one over here. This is all not incorporated, and this is going to be incorporated. Okay? So this is at Lyndhurst, not incorporated. There's our control, it's pretty acid, and it's acid to depth. Where we put on, it's 2.8, so say 3 tonnes. So this is close to what current practice would have been at 2.5 tonnes a hectare. Surface applied, that's that line. And you can see it's done bugger all other than change the pH at the surface. And then these blue ones, sorry.
Yeah, red, green, blue.
Green is 4.7 tonnes, say caught 5, and blue is 6 tonnes a line. Not incorporated, just thrown at the surface. Incorporate by sowing only, okay? That's 1 year after application. This is the same lime treatments, but incorporated, except for the black diamond now is this once in a generation. And it was 7 tonnes. Okay? So what do you see? Incorporation helps, right? It gives you a head start, yeah? So all of these are further this way than over here. And that extra tonne of lime here, you saw the benefit. So it's about 0.6 of a pH unit better here than the next 7 tonne is about more than half a unit better than 6 tonne. So what I take away from that is, if you are going to incorporate, this was all horse tiger incorporation on this trial. Wherever it says incorporate, this is all horse tiger. So the difference between here is lime, the amount of lime you put on. So it costs the same to run that machine through it. You had the same erosion risk and all the things that come from that sort of cultivation. And what I'm saying here is reward that cultivation by putting on enough lime to get the change you want. Okay, so that was 2021.
That was incorporation to 20 centimetres.
Yep.
Well, measuring the tip of the horse tiger, the depth of the penetration of the horse tiger.
So on the left now, that's 2022 data. coming in. Rightio? And so not much has changed, yeah? And where we incorporated, rightio? And so incorporation definitely gets you a head start, and if you're going to do it, put on enough lime to make a difference. Fair? Now, and a question from, it was up the, you were up the back before, weren't you? Yep. Yeah. So should I put 2.5 tonnes on and get a horse tiger and incorporate to 20 centimetres? No. Why? Because you're running all the risk and all the cost of cultivation, but you haven't put enough lime to make the difference. That 2.5 tonnes, there it is at the surface, okay? If you cultivate that in to depth, all you're doing is diluting that lime out. And so you'll have the cultivation, but you won't get the pH coming up high enough. When you put on enough lime, you get the pH up, and then there's excess lime in the system, excess alkali. It's above 5.5, so all of this stuff can still move down. With me?
If you've got large numbers of stock, with high concentration, with dung beetles, the dung beetle holes help incorporate the lime.
Yep, so, and worms do it as well, right? The issue is the reliability of it and how...
Yeah, I wouldn't know, that's right, but I'm a bit thinking long term. You've got good...
Yep, it helps, it helps. It helps, but we're calling this cultivation once in a generation.
Yeah.
Yep. So I would say you set up once in a generation, put enough lime on, mix it in well. Yep. You set yourself up for a future where you don't have to do that again. You've got no acidity in that zone, so all your biology is much better off, and you're much, your
system's functional.
Your system's functional. You'll have worms that can survive. Yeah. You'll have dung beetles that can actually do what you say. It's going to be better than having this acid layer that won't let roots through, which will get hard and stop that sort of activity.
We're getting wind up a little bit.
Yep.
This once in a generation with high rates, people are doing this because further south, $9,000 an acre for land, whether it's got pH profiles like this or not, they're talking about how many more crops they're going to be able to grow. Are they going to be able to establish Phalaris and clover to make it pay? So there are, and that was the philosophy that people, or the thinking that people did not have in the 80s.
And it comes down to resilience as well. Like think about that, the plants growing in that don't have the stresses that are growing in this. Plants growing in this will resist bad starts, dry springs, environmental crappy years.
This is just a shot of some of the roots from a treatment down at Holbrook. Maybe I might just move on. So what we're just basically saying is that nil lime, the plant's stressed, the system's stressed. As you add lime, top dressing, you're getting that sugar hit. It looks good short term. You're not going to be getting resilience through tough seasons. Where we incorporate, we've got better root systems. And this is the once in a generation rate down at Holbrook site, 6 tonnes per hectare. No signs of any deficiency symptoms showing up there. What we also found was we did some nitrate measures on this. And the nil lime, look at the parts per million, 350. Nitrate levels low. Where we had the higher rates not incorporated, 1,500 parts per million. Where we incorporated with the higher rate, the highest rate, almost 2,000 parts per million. And there's a lot there related to plant metabolism, efficiency of use of nitrogen. Are you actually wasting nitrogen, putting on the same rate of nitrogen on this plant as you are on this plant? So there's lots of discussion there that we would like to do some research on, but it's all to do with the nutrient use efficiency, effective functioning of the plant. Now, this is, we were just going to talk about the different rates for the different systems that or the different soils that we've been treating. We've got Lyndhurst, which is the really acidic site, Morven down at Holbrook, and Tugong.
So this slide, it's here because it's an important take-home message for you. right? So far, I've spoken about getting your pH up over 5.5, and it's more lime than you used to do. Fair? Right. That amount of lime, I don't want you walking away thinking, oh, we have to put on more lime. That's the solution. Jason's what he's talking about, yeah, we have to put more lime on. It's not the case. It's all about the target pH. How much lime it takes to get there is where you're at now. And this slide speaks to that point. So there are 3 sites. You can see the range of acidity in that 5 to 15, that zone where the curve is most acidic. And you can see that these things are the rates, the target treatments that we had. You're familiar with that? Yep. And so to hit these, you need rates of lime. And that's what the table is. You got me? 3 different sites, different acidities, same targets. Which is the best one? This is pretty bloody good. And this one is good also. Fair? Because it's giving you long-term benefit. Alkaline moving down, because we're over 5.5. That's the data. Tell me, what do you see? What do you see?
If you let it get to acidity, acid, you have to put a lot more.
Yep. To hit the same target, if you wait until you've got a problem soil, it's going to be an expensive problem. If you look after your good soils that aren't basket cases at the moment, even once in a generation, it's not ridiculous quantities of lime. That sets you up into the future so you don't have a problem. You with me?
That Tugong site, it comes in pH at 5, around about 20 centimetres. These are all acidic, down to 30 centimetres. So this is an early intervention to prevent that subsurface acidity going deeper.
And so this is like, in my mind, this is like you've all got tractors, you change the oil in the tractor, you do maintenance, it has a cost, but you're doing it so that you don't have a catastrophe. This is the catastrophe. This is, you're replacing the engine now, right? So change the oil, maintain your soils, look after them, so you don't have expensive intervention later on. I work with a guy from WA who's done lots of stuff with acidity, and because WA is sandy, their problems happen earlier and they happen deeper, okay? And he said, Jason, the most important message that you can give land managers in the East is don't let your soils get so acid that they become too expensive to fix. In their benchmarking studies, it said there are 2 groups of farmers, those that lime and are productive, and those that don't, who are now in trouble. And I said, what do you mean by that? Like, what's the trouble? He goes, the acidity is so bad that it's moving down deeper. They've lost productivity, so now they can't afford to lime, and no one wants to buy their property. Right? He said, don't let people get to that. And that's this if nothing's done. That's where you're going with that. You're getting to the point where no one's going to want that. Whereas if you maintain good soils, it doesn't get to that. Agriculture is acidifying, and the sooner you address that acidity, the cheaper it is, the better bang for buck, and you're future-proofing your agricultural productivity.
We're not picking up any production or visual symptoms of response in this site. That's good. That means that we haven't, that we've come in early intervention before there's productivity loss. Those other sites, we're getting 50% yield increase. Or, in the case of Lyndhurst, just totally different pasture composition.
How many of you have heard, well, let me ask you a question. Does liming pay? It does? Does anyone want to tell me it doesn't? Or it takes too long to worry? Yeah? No? Like,
John?
Yeah,
Well, in certain circumstances it
such as?
Well, if I've got a low stocking rate grazing soil on inaccessible country,
Okay.
the marginal increase in stocking rate of 30% won't be adequate to warrant the investment of lime.
So what happens to that land though, long term?
It remains low productivity.
It degrades though.
Yes,
Yeah.
but But I don't know, does it hit equilibrium at some point?
Well, the Western Australian experience is that it will keep acidifying. The rate will slow down because the system becomes less productive, but the acidity moves deeper down,
Yeah.
and then you lose species diversity.
Yeah.
Yeah.
Probably becomes a bit away sand.
Yeah. Look, I'm just going to do that to you, which is a bit horrendous, I understand that. What this is a bunch of trials, the enterprises that were run on them, the response to lime, so all of these trials were replicated and they had with and without lime to compare. So all of them had gains in productivity, and at the time, gross margin was reported, and some of them lost money. And so in some places you go, people talk about, oh, lime doesn't pay. Anyway, so that's what this table is. Now that table there, that column, is all based on the economics of the year that this stuff was reported. And so in some cases it's back in the 2000s, okay, or early 2000s. Now, what I want you to focus on is this gain in DSE, carrying capacity. In some cases it's productivity, but in a lot of these cases, and John will talk about this, those gains were around 20% gains in productivity. And my point about including this in there, this doesn't matter what year it was, a 20% increase in productivity is a 20% increase in productivity. The economics is what changes, the commodity price changes. And so this is almost irrelevant. You put that productivity gain on today's economics, then you can compare it. And so this trial by Matt Lischke, which was 2021, close
On native pasture.
On natives.
Native with clover.
So three DSE increase was $180 increase in gross margin. And so that, you look up here, back in the day, it was $25 because commodity prices were rubbish. Okay, so the notional line doesn't pay. You need to look at the productivity gain, look for evidence of productivity gain, if you like, but put it on make sure you look at today's economics.
Those bottom three were all native pastures with subclover, naturalised subclover.
And that drive, so this is Matt Lischke's work at Lagan. You got the gain when you needed the feed. You got the gain in autumn above your control. It's a big difference. And he actually did a great bit of work. He actually showed it was the clover responding to the lime, fixed nitrogen, drove the system. Okay, so it had clover in the system as a really key part. And just finishing up now, I always like to finish on this. This is at the University in Wagga. This is a trial that had lime in 1989 on plots this way. And this photo was taken during the drought in early 2000s. And this is lucerne. So that liming event was giving productivity responses that were still evident 20 years later. So liming pays you back when you need it most, in this case a drought. And that feed, that green feed where the lime was worth a lot to that enterprise. You imagine it, We saw it here because we've got this comparison. These are field peas, 3 times the productivity where the lime was 20 years before. And if you didn't have that comparison and you just had this bit in here, you'd think, oh, peas kind of sucked this here, didn't they? But it's just because it didn't have the lime. In summary, agriculture is acidifying, yeah? You're right. The better you are at farming, the more acidifying you could be. Sampling in 10 centimetre intervals doesn't find stratification. And people say, oh, but it's hard to do 5 centimetre increments. It is, but you get a number that means something. And so measuring soil in 10 centimetre intervals, I always say it's kind of like me having an opinion in my house. I can have it, it doesn't mean anything, it's worthless, right? But 5 centimetre intervals actually tells you something that you need to know. And at worst, it gives you a false hope. You put lime out, the pH went up, you think the job's right, but in actual fact, you've still got this acid layer there causing you problems. Our old topsoil targets are too low. Liming's to get rid of the aluminium isn't doing anything to address acidity deeper. And so we need to increase our targets keep the pH above 5.5. Keep 5.5 is our reliming trigger. So pH in the 0 to 10, keep it above 5.5 and you'll get movement down. If you know from your 5 centimetre interval sampling, if you know that the acid layer is at 10 to 15 and after that the pH goes up and I don't have a problem anymore, then you only have to get alkali moving into that layer. Okay, so you could mix it in with incorporation, or you could keep this at over 5.5 and within 5 years that would be fixed.
So it'll be that long, like that 5 years.
Based on what we've seen, it's going to, that's a piece of string, right? Because rainfall, how acidifying your system is. Yeah. How do you know? Test it. Test it. Do soil testing and find out. Incorporation definitely gets you a head start, right? But our depth of incorporation and our mixing of lime is never as good as we think it is. Okay, so it's definitely a head start. If you are going to incorporate, definitely reward that cost of incorporation and the risk that's associated with erosion and that sort of stuff. Reward that risk by putting on enough lime to get the pH change that you're chasing. And again, 5 centimetre intervals help you find how bad the acidity is, where it is, and then based on that you can work out how much lime you need to get the job done. So look for it, measure your pH. We are very fortunate, we have a bunch of people who help us find sites, manage them, run experiments, so really grateful to all the people who help us, especially the landholders that allow us to run trials on their land. So thank you.